Okay, we are here today to guide you through the rheological experiment, and we mainly use rheology for characterizing viscoelastic materials. But first, where do we find viscoelastic materials? If you think, we can find them everywhere, ranging from the cosmetic industry, food industry, and also 3D printing material. Today, so we are gonna characterize them, and they are really interesting because we have these materials ranging from purely elastic to purely viscous, and we get them both properties in these materials. So what we use to characterize these viscoelastic materials is a rheometer, which is working on shear directions and not normal direction as in common compression and tension experiment. So we have different options, and we're gonna squeeze our materials through different geometries. We have here, for today's experiment, we're gonna use cone and plate geometries. Then we're gonna mount first our device on the rheometer. First of all, we need to align the notch, the black one, the lower one, and the top one. Once this has been aligned, just fix it, and we are ready to calibrate the machine. First of all, we need to reset the force to compensate the weight of our measurement system. Once the force is set to 0, we can then set the zero gap. The zero gap is extremely important because we need to know the exact distance between the two geometries and then the thickness of our sample, because then based on that we can calculate the shear strain applied to the material. And for today's experiment, we are going to use Rheology, which is a 3-block polymer formed of a hydrophobic center for polypropylene glycol and two hydrophilic polymers, polyethylene glycols. Based on a specific concentration and temperature, they are able to assemble, forming a micelles and resulting in a gel formation. Once the zero gap has been set, we can then load our sample between the two geometries. This point is important to match more or less the exact volume we need to have, so that we don't waste too much material. So for the first experiment here today, we're gonna use 23 weight% Rheology, and we're gonna extrude exactly in the middle of the measurement system. More or less 300 microliters. At this point, we can pull down the geometries and work at a specific distance of 0.105 millimeter. Okay. And then once it's set, we can start remove all the excess of the materials, because we don't want that the machine is thinking that we have more material, stronger materials, since we need to know exactly the surface area of our geometries, and then based on that we can calculate the shear forces. At this point, we use a blue plastic spatula to not stretch the PLJ plate. At this point, then we can raise the passive foot down so that we isolate the materials from the environmental conditions like temperature and as well how dry the air is. At this point, then we can continue with our test. Then, as a first test to do is the shear strain that my colleague is gonna introduce you.
Once we start the test, we need to name it with the test date, sample used, and setup remarks. Then we need to move to the test steps. First, we start measuring the properties of a gel in oscillatory mode, because we are interested in the elastic and viscous components or storage and loss moduli. In your dataset, you will find the frequency sweep measurement, but we skip it here as it takes 1 hour. As my colleague mentioned, we start with a strain sweep where we keep the frequency constant and increase the strain to see the yielding phase of the material. At the beginning of the measurement, we will see a linear viscoelastic regime, so that the storage and loss modulus are at constant values, even we are increasing the strain. However, at some point we will see some changes. So what do you expect to happen to storage and loss moduli as the strain is increasing? Try to sketch it. Once this test is done, we move on to strain recovery measurement, which has multiple intervals. First, we apply a low strain amplitude to measure the initial properties of a gel. In the second interval, we apply a high strain amplitude for a specific amount of time, and then we go back to the initial low strain. At the beginning of the measurement, we see that both storage and loss moduli are at fixed values. Based on what you have seen in the previous test, try to sketch your prediction of what would happen if the rheometer jumps from low strain to high strain. We see two changes in the material. First of all, there is a significant drop in both moduli In addition to that, they are reversed in position. You could think about why we see such results. In the next interval, the strain will go back to low value. What do you expect to see? Is the gel network broken irreversibly, or can it recover part of its integrity? Sketch your prediction. Floronic gel is a viscoelastic material behaving as non-Newtonian fluid. This means that at high enough concentration it will be a gel, but once a force is applied, it could be extruded or switched to liquid-like. After removal of a force, it goes back to gel state and maintains its shape, as you can see in this video. To measure such behavior, we can do a shear rate ramp. It is a measurement done in rotation mode, so you will see the geometry moving with increasing rotation rate. What would you expect if we deform this material faster and faster? Would the resistance to flow increase or decrease? Sketch how viscosity profile may change with this increasing shear rate. Next, we move to a stress ramp, where we don't control the velocity of deformation, but the stress with which we deform the material. We know that Floronic has a yield stress, which means that the material starts to flow only once the stress has been overshooted. What is the relationship between the previous measurement, or how do we express and relate shear rate ramp and stress ramp? Up to now, all measurements were done at room temperature. In a temperature sweep, we apply a constant strain amplitude and constant frequency, but we decrease the temperature of the material. Based on what you have read in the script, what would you expect at low temperature to happen? Sketch the material properties.